Today we are again, we'll continue the last lecture, which was about training these neural networks or these CNNs. And we started with like the general idea how we are going to train these networks. And then we talked about the optimization algorithm, that is the stochastic gradient descent. So today we'll continue on that, and the next segment will be backpropagation. And again, this is like a very, I would say, a broad topic. It will take a lot of time, so we'll just touch upon the basics of what backpropagation is and how it plays a role in training on networks. Now, before starting that, let's do a quick recap of what we did in the last lecture. So we were talking about optimization, and given a function, the idea is we want to find a place in this function or the response of this function where the value of this function is minimum. Okay, so that's like a high level idea of what optimization is. And in our case, this function is the loss function. All right, so the loss function which we will write, which will tell you how good your network is performing. Okay, and that we will do because we have the network's prediction and we have the ground truth. So we'll make comparisons and we'll formulate some kind of function which will say, okay, this is the loss value and how this is like how good the network is doing. This is how bad the network is doing. So that's the loss function in our scenario. And the idea is we want to find like these minima points because we want to minimize the loss. Okay, we want like the prediction of the network to be as close as the ground truth. If that's the case, the best case scenario is your loss will be 0. Okay, if your network is actually performing perfectly. So that's the high level idea. We want to minimize that function. And as we discussed, like that loss function is never going to be like a simple convex function. You might have a lot of minima there. In this case, this is again a simple one-dimensional function. It has two different minima. So one at this point and one at this point. So these are called local minimas. So usually like the loss function for neural networks, it will be very complex. So we'll have a lot of minimas and hardly there will be like a global minima. Okay. Now, the idea is we want to reach to this point, and as we discussed in the last lecture, we are going to make use of stochastic gradient descent. The idea is we initialize like our network randomly, which means that the initial prediction will be random. So with that random prediction, the loss value will be high because it will be just a random guess. All right. So in this case, let's say you initialize your network with A1. Your loss value will be something like this because that's your loss curve. And the goal is we want to move this point in this direction and reach this point. Okay, so then your loss value is actually reducing from this level to the minimum level. And your network parameters are actually going from A1 to A stop. Okay, so to go from this point to this point, this is the simple equation, which is like a single step of your gradient descent algorithm. And as we discussed last time, there are a couple of parameters here. The first is, you can look the second term here. This is just computing the gradient. Okay, so we'll find the gradient at this point, and that will help you determine like which direction you want to go, whether you want to increase the value or you want to decrease the value. Okay, so you will use the gradient, and then you have another hyperparameter, which is gamma over here, which is the learning rate. It will control how fast you want to move in either of these directions, either left or right. Okay, so this is kind of trying to control the step size as you move from A1 to A2, A3, and A stop. And eventually, if your value is not changing, because in this case, the gradient will be almost 0. So if you're not changing, that's the stopping criteria. And you say, okay, you have reached the local minimum. And that's when your training ends. Okay, so that's the high level idea. Now, to be able to do so, you know that we were using that simple equation that was like a one step for gradient descent. So to make that one step, we need to compute the gradient. Okay, which means that whatever like functions you have like in your network, you should be able to find the derivative of those functions. Okay, so this is a very important point. So let's start from the end where you have the loss function. Okay, so first of all, you will have to find derivative of your loss function with respect to the parameters. to be able to find that gradient. And to be able to do that, your loss function should be differentiable. And as you know that not all functions are differentiable. So you'll have to come up with a loss function, which is actually differentiable. Okay, not just that, as you move further down in your network, because you are going to find the gradient of your loss with respect to those parameters, which means that everything inside your network should be differentiable. And that's the only way you will be able to find those gradients, because you can't differentiate like discrete functions, right? So which means like you have activation functions in your network, they should be differentiable. You are using the convolution operation or the correlation operation when you are actually moving from layer to layer using that filtering operation, right? So that operation should be differentiable, and we know that convolution or correlation is differentiable. Okay? It's just like linear combination of those pixel values. And any other operation you are performing inside your network, for example, you are performing pooling, that should be differentiable. We know that max pooling is differentiable. And that's one of the reason, if you remember, like when we were talking about filtering, then we came around one very interesting filter that was median filter. And we saw that it was performing pretty well. It was able to get rid of all the noise in the image, right? And the issue is that median operation is actually not differentiable. So that's one of the reasons why we can't use median filtering in our neural networks. And again, that's just one reason. In computational complexity is the other main reason. Okay, so the bottom line is, when you design your network, everything you are using inside your network, it should be differentiable. You can't just plug in like any non-differentiable function inside your network. All right.